Okay, welcome back, class. And today we are going to continue on and we're going to talk about section 3. So 1.3 is about complex numbers. Okay, so this is all about concepts of complex numbers, basic concepts, and operations on complex numbers. Okay, so there is no real number to the solutions of an equation to this, right? So what we mean by that is there's no real number that we can put into x that will give us a negative number. Why is that? Because any real number that we stick in for x, when we square it, is going to give us a positive number. There's no way to get a negative number. So we say that there's no real solution. Okay? That's where complex numbers come in, because there may be there is a complex solution. Okay, so now complex numbers are a bigger set than real numbers. In fact, as we've discussed, complex numbers includes real numbers. So that's where we're going to start with. Okay, now we have to define, when we're dealing with -1, we're going to define a particular number, and we're going to call this number I. And so when we solve for x here, we're going to get x is equal to plus or minus the square root of 1, right? Because we're using the square root property here. And so we get x is equal to plus or minus the square root of -1. So we're going to define the square root of -1 as a special, denoted by a special symbol, I. And so I is equal to the square root of -1, not plus or minus, but just the square root of -1. And so I squared equals -1. So now we've got a way to deal with what we call complex or imaginary numbers. So now, if A and B are both real numbers, then any number of the form A plus BI is a complex number. So that means any real number is also a complex number. Okay, so we could have A is equal to 0, and then we just have the imaginary part, the imaginary number. Okay, and then, or we could have B equals 0, and then A is just the real part, is a complex number. So every complex number has a real part, A, and an imaginary part, B. Okay. Now, two complex numbers are equal provided that their corresponding parts are equal. In other words, this is going to be equal to this if A is equal to C and B is equal to D. Okay, so this is the definition. So this is true if and only if this and this are true. Okay, so it goes both ways. So that's the definition of two complex numbers being equal. Now a complex number, right? So if you have, for a complex number, we have, if B is 0, just like I said, you get A. So as I said, the set of real numbers is a subset of the set of complex numbers. If A is 0 and B is not 0, then we have a pure imaginary number. Okay? So a pure imaginary numbers would be something like, if we have 7 plus 2y, right? So a pure imaginary number. So a pure imaginary number, or a number like this, right, where A and B are both not equal to 0, is a non-real complex number. Okay, because here, right, this is a non-real complex number. Okay, now a complex number written in the form of A plus BI, okay, or if you want to switch it, a plus ib, it doesn't matter, where you normally put the b in front, is standard form. So a plus bi is the standard form for any complex number. Oops. So if you look at this, look at the way this works here. So this slide gives you a perfect picture of the relationship between all of the sets of numbers that we will deal with in this class. In fact, in any class, okay? So we have the natural numbers. Those are the counting numbers. It starts with 1 because that's what we count with, right, when we're counting things. So the natural numbers are 1, 2, 3, and 4, and so on. Now, if you want the whole numbers, all you have to do is take the natural numbers and add 0. So whole numbers are the natural numbers, and then you include 0. Okay. Now, if you want to go to the integers, well, that includes all whole numbers, but then you're just going to put the negative sign to all of them. So you take all the whole numbers, right, and then what you do is you add the negative signs to the natural numbers. So that gives you the set of all integers. You don't put the negative sign on 0 because 0 is neither positive nor negative. Okay. Now you have the set of integers. Now integers are not fractions, right? They can be expressed as a fraction, but they are not fractions. Okay. So if you want to include fractions, now you're going to increase to the rational numbers, because all integers can be expressed as a rational number, but not all rational numbers can be expressed as an integer. So if you add all of the fractions, right, all possible fractions, then now you've increased from integers to the set of rational numbers. Okay, now these are all subsets of each other, right? So now there's another set of numbers that is completely disjoint and separate from rational numbers, and those are irrational numbers. So rational numbers are all numbers that can be either written as a fraction or a terminating decimal or a repeating decimal. Okay. Irrational numbers are any number that cannot be written as a fraction, and those are the irrational numbers, like the square root of 2, or pi, or the exponential, the natural exponential e. Okay, so these are the set of irrational numbers. Now, if we put the irrational numbers plus the rational numbers together, well, guess what? That gives us a subset of the real numbers. Okay? Okay, so far so good. So rational numbers plus the irrational numbers gives us the set of all real numbers. Now, if we look at the real numbers, right, that's where b is equal to 0. So again, so we're taking the general idea here. So all complex numbers, right, can be written in this form. So real numbers are where the imaginary part is 0. b is equal to 0. So this is gone. So we just have a. So that's going to be this part. Okay. Then we have the non-real complex numbers where b is not equal to 0. And so that's going to be these. Okay. But if we put these together, they're all complex numbers. Okay. But inside here, right, inside here, if you want to get technical, we have the pure imaginary numbers, which is a subset of this because that's where just a is equal to 0. Okay, so these are pure imaginary numbers, which are inside the non-real complex numbers. Okay, and then of course, all of these numbers together form the complete set of complex numbers. Okay, now the expression of some value of square root of negative a. Okay, well, we can represent this as in terms of I, because we could always represent any negative value, any negative number, as some positive number times negative 1, right? And we can always use the square root property and split it up into a product of two square root signs. Okay, so in other words, we can do this. Okay, this is going to be equal to the square root of -1 times square root of a. And so then that gives us I, and there's the square root of a. So there you go. So let's look at this example. So A says we want to write the square root of 16 as an imaginary number. We want to simplify it using I. Okay. So what we do is we rewrite the -16, right? The negative part. So this is -1 times 16. And then we split it into the square root of -1, which gives us I times the square root of 16. And the square root of 16 is 4. So we get 4 times I. And we're done. How about the square root of 70? Again, split it up into two pieces. So this is going to be the same as the square root of -1 times 70. So we can write it as the square root of 1 times the square root of 70. And so the square root of 1 becomes I, and we get I times the square root of 70, and then we want to see if we can simplify the square root of 70. Okay. Now, are we able to simplify the square root of 70? No. So what about this one? So again, this is going to become what? I times the square root of 48, which is equal to 16 times 3, right? So that should be times. And so we get I, and this is going to be 4, so we could split this up into the square root of 16 times the square root of 3. Well, the square root of 16 is 4, so the 4 comes in front, and we get the 3, square root of 3 stays there, so 4I times the square root of 3. Okay, products or quotients with negative radicands are simplified first by rewriting with I, and then we're going to simplify. Okay, then we're also going to use the fact that this I squared is equal to -1, right? And so we're definitely going to use that to our advantage to help simplify things. Now, when working with negative radicands, use the definition of this. Okay, so this is what we're using before using any other rules for radicals. So do this first before you do any other rules or properties of radicals. So here's another question. So in particular, the rule that this equals this, which is true, okay, that is true, okay? We know this is true, but this is valid only when C and D are not both negative. Okay? When C and D are not both negative. When they are both negative, we want to make sure that we change it to this, because watch out. If we do this and we put them together, we get -4 times 30, times 9, which is positive 36, which gives us a positive 6. That is not correct. Okay, so whenever you have negatives, always change it to the imaginary number with I. So you're going to want to change this to I times the square root of 4, which is 2I. And this is going to be what? 9I, and excuse me, 3I. And then 2 times 3 is 6I squared, because you got two i's. I times I is I squared. And so now I squared is -1, which gives us a -6. Okay, so be very careful with this. So now all we're going to do is change this to I times the square root of 7 times I times the square root of 7. And then what are we going to do? We're going to group the i's together because it's multiplication. Okay, so this box, don't worry, this is multiplication. It didn't come through right. So this is going to be I squared, what gives us a -1. So what are we going to get? Ooh, well, what happens here? This times this gives us what? 7. So we're going to get a -7, right? Okay, so make sure you understand what happened there. Now what about here? Here we're going to get this times this, right? So what are we going to do? We're going to split this up into the square root of -1 times 6, -1 times 10, right? Then we're going to split it up and we're going to change it to I, right? So we get I times the square root of 6 times I times the square root of 10. Well, now I times I is going to give us I squared, which is -1, right? And so then now we're going to look for ways of simplifying underneath the radical. Now that it's positive, well, we can change this to 4 times 15. And 4 is a perfect square. That's what we're looking for. We're looking to split this up into two factors where at least one or both are perfect squares. Okay, or this might be a perfect square itself. Okay, so here we got 4, and that's a perfect square. So we'd split this up into two radicals. So we get the square root of 4 times the square root of 15. And then we get 2 times the square root of 15, and there's nothing more we can do with this one. There's no other perfect squares in there. And so now we get negative what? -2 times the square root of 15. And that's our answer. Now let's do the same thing when we're dividing. Okay? So again, we're going to change these two in terms of I. So this becomes I times the square root of 20, I times the square root of 2. And now what we can do is we could take this, right? Now the I divided by cancels each other out. They go away, right? This equals 1. And now we can use the property of radicals and combine the radicals, the quotient under the radical. And what do we get? We get 10. So we get the square root of 10. Okay, what about this one? Okay, so same thing. We're going to take the I, right? And now we get I, and we've got this now. Now we can focus on this. Okay, so we get I times the square root of the quotient. And so 48 divided by 4 is 2. And so we get the square root of 2, which cannot be simplified any further. Okay, now what about this? Okay, well, the first thing we're going to do is we're going to write this in standard form, right? That's what they want us to do. Okay, well, we've got to have two pieces, right? We've got to have the first piece, which is the real piece, and we've got to have the imaginary piece. Well, the easiest way to split this up is to split it up into two fractions. So here's your plus sign, so you're going to have this divided by 4 plus this divided by 4. So you can split this up into two fractions, right? Because you have a common denominator. Okay? So that's what we're going to do. So now, what are they doing? You're going to split this up. Okay, 128. You can split this up into 64 times 2, right? 64 is a what? Perfect square, which gives us 6. But there's a negative sign, so that's where our I is going to come from, right? And so -8 plus 8I times the square root of 2. Okay, so make sure you understand how we got to this part. Okay, now we're going to split it up into two parts, and we're going to get a -2 and a +2. Okay, so you factor out a 4, right? Why? Because it canceled with this 4 down here. Okay, and you get the same answer I just said. -2 plus 2I times the square root of 2. And this is the simplified form. And you always want to have it in lowest terms. You never want to leave it as a fraction if at all possible. Okay, always simplify it as much as possible. So now, here are the addition and subtraction properties. Okay, so for complex numbers a plus bi and c plus di, you can add complex numbers by adding corresponding parts. Add their what? Real parts, and then add their imaginary parts. So you always add corresponding parts. So a plus c, and then b plus d, and the I goes with, then you factor out the I, right? And then subtracting, you got to be careful because when you're subtracting two of these, you've got to distribute the subtraction. Okay, so it's going to be, this is a minus and this is a minus. So when you're subtracting complex numbers, you subtract corresponding parts. So it's going to be a minus c plus b minus d. And so that's what you get here. And so now let's use some examples. Okay, so real quickly, what am I going to do? Well, I'm adding, so I'm going to add corresponding parts. So I'm going to add the real parts, and then I'm going to add the imaginary parts. So I'm going to add 3 and negative 2, and I'm going to add negative 4 and positive 6. And then again, the i's go with the i's. Okay, and so what do I get? I get 1 plus 2i. Okay, just make sure you understand what we did. Okay, what about this one? Now we're subtracting. So the first thing I would do is what? Distribute the subtraction, right? Or what you could do is change this to a plus and then and then distribute the negative sign. So it'd be plus negative 6 plus 7. You could do it that way. But again, make sure you subtract corresponding parts, and then this changes to a plus sign. So this becomes this minus this plus this minus this. Okay, and then of course the I. And then this is what you get. Now, the product of two complex numbers is found by multiplying as though the numbers were binomials. So the way you handle complex numbers is like when you using the distributive property or using the FOIL method when you're multiplying binomials. Okay, but in this case you're going to use the fact, because this will always happen, you will use the fact that I squared is equal to negative 1 to simplify it when you're done foiling or using the distributive property. And so this is the way it's going to work out in general. So you multiply the first, you get AC, then you multiply the outside, so you get A times DI, and then you get B plus CI, right? And then, times CI, and then you get BI times BI, and then you use the commutative law to move things around, and then this is where you get I times I, which is I squared. And then this is going to add together, so you're going to get AD plus BC times I, right? And then, right, there you go, there's the I squared. And so then you're going to factor out the I here, and you get this. And this is going to become negative 1. And so then your final answer is you're going to get this. So notice what happens here. Okay, this becomes negative, so you get AC minus BD, and then you get plus AD plus BC. Okay, and then this is the general form. Okay, so all you're doing is using the FOIL method or the distributive property, and then simplifying. Okay. Now, for complex numbers a plus bi, this is always true. So as long as you know a, b, c, and d, this is always equal to this. Now, I would not try to memorize this. I would just use the FOIL method and just simplify. It's not that difficult to do, okay? But this is always true. So now, let's find the product of each of these. So the first thing I'm going to do is we use the FOIL method, right? So see what we get. So we use the FOIL method. So 2 times 3, and then 2 times 4i. and then 3 times negative 3i, and then 3i times minus 3i times 4i. Okay, so again, we just used the FOIL method. And now what we're going to do is we're going to use the commutative property here and put the i's together, right? And so we're going to get I squared, which is negative 1, right? And then, of course, we're simplifying these, right? So now we got this. And so now what we can do is we can add, right? We could combine like terms, right? So we have 8i minus 9i, which is going to give us what? A negative I here, right? So then this is negative 1, right? And so now we're going to simplify. So now this is going to be a plus 1. And then add it to the 6 and we get 18. Okay? And so our final answer is 18 minus I in standard form. Now what about this one? This one is a little tricky maybe, but we're going to treat it, we're going to take the definition of an exponent, right? So what does it mean? It means that we're multiplying by itself twice, right? So it's this squared. So we're going to still use the FOIL method because it's going to be this times this, 4 squared, and then it's going to be 2 times 4 times 3i because we're doubling this, and then we get this. Okay, so this is nothing more than the square of a binomial. And now we're going to simplify things, right? Okay, and then this becomes negative 1, right? And then this is going to become negative 9, and we're going to add it to the 16, or subtract it from the 16 if you want. And then we're going to get 7 plus 24i, and we're done. Now what about this one? Now this one is another special one. Okay, we have 6 plus 5i, and then 6 minus 5i. Let's see what happens here. So we're going to, again, do the FOIL method. And what happens? Well, the middle term falls out, just like in binomials. Okay, so we end up with the difference of two squares, right? So it has the same sort of form as the difference of two squares. So that's what we're going to get. We're going to get 6 squared minus 5, the quantity 5i squared. So what happens here? Well, remember the properties of exponents. We're going to distribute the square to both of these, 5 and the I. Okay, so we're going to get 25, and then I squared is negative 1. And so again, this negative 1 is going to change this sign, and we get 36 plus 25, which gives us a real number, right? Because I is 0. Now, if we want to write it in standard form, this would be correct, right? So this is 61, or we would write it, if I asked for standard form, 61 plus 0 times I. Okay, now, we showed that that difference to squares equals 61. Okay, so what these are special pairs of complex numbers, and what we call them is we call them complex conjugates or conjugate pairs. Okay, the product of any complex number and its conjugate is always a real number. Okay, this is going to be helpful in solving problems or equations that involve complex numbers. Okay, so this product is the sum of the squares of the real and imaginary parts. So we have this form. So you can memorize this just like the difference of two squares. This is always going to be, when you have a plus bi times a minus bi, you're going to get a squared plus b squared, because the i's are going to go away. Oh, and notice that, hey, when you factor things out, when you're dealing with polynomials, and you get the sum of two squares, we always say, hey, there's no real solution. Well, guess what? Now you know what the complex solutions are, okay? Because it'll always be a conjugate pair. Now, let's find the quotient for this one. Okay, so now, how are we going to find the quotient? How do we find the solution here? This is where we're going to use the conjugate, okay, to solve this, because we want to get the I out of the denominator, okay? So the first thing we're going to do is we're going to multiply the top and the bottom by the conjugate of the bottom. And we can do that because what's this divided by this? It's just 1, right? So we're just multiplying by 1, which doesn't change anything. So this is a technique of being able to solve these without changing the fraction, right? Because we can multiply the top and the bottom of any fraction by the same number, and it's still the same, right? And so what happens when we use this? Well, the bottom is going to give us the difference of 2 squares, right? And then the top, we're just going to use the FOIL method, and we're going to simplify, right? So this is what we get. Okay, so notice this gives us what? 25 plus 1. And then this is going to be negative 2 plus 15. And then this is going to give us 13. And so we end up with this. 13 plus 13i over 26. Now notice that we can factor out a 13 on the top, right? Or you could split it up into 2 fractions. Same thing. Okay, so the 13 it goes into 26, right? And so now we get 1/2. So we get 1/2 plus 1/2 I, and this is the way we would leave it. Okay, we can't simplify it anymore. And so now we're going to check. Okay, so now what we're going to do is we're going to take this, okay, and we're going to stick it back into the original problem and see what we get. So we take 1/2 plus 1/2 I times the conjugate, or times 5 minus I, right? And what do we get? We get 3 plus 2I. Okay. Oh, hold on. Okay. So we got right back to what we did with the denominator. So this is the same as this, right? Or if you, never mind, you don't want to do it that way. But yeah, so all you have to do is multiply the top and the bottom, right? Multiply this by the denominator, right? And you should get back to the original numerator. Okay? So now let's do this one. Here, what's the conjugate of I? Minus I. So we're going to multiply the top and the bottom by minus I. And so we get negative 3i divided by what? Negative I squared. And so the negative and the negative are going to cancel, so we actually get 3i over I squared. Right? Now, what you don't want to do is go backwards and cancel, because then you're going to go backwards, and you don't want to do that. So what we want to do is we want to use the definition of I squared, which is 1. Okay, or negative 1. But then it cancels with the 1 here. Either way, you're going to get negative up here. So what do you end up with? Oh, negative 3i. Or, in standard form, 0 minus 3i. And then, of course, check. Now, the powers of I can be simplified by using facts. Okay? The powers of I are cyclic, meaning I is equal to the square root u of I, right? And then I squared is negative 1. And then I to the third is what? Negative I. And then I to the fourth is 1. And then what happens to the I to the fifth? You get I again. So there's a pattern here. So as long as you can remember the pattern, then you can always reduce any power of I to one of those 4 outcomes. either I, -1, -I, or excuse me, I, I, -1, yeah, -I, or 1. And so here it is. I, -1, -I, 1. I, -1, -I, 1. See how it's patterned? So every 4, it starts to repeat. 1, 2, 3, 4, 1, 2, 3, 4. And it keeps going. So this is going to be very powerful in helping you. So I to the 0 obviously is 1 because any number raised to the 0 power by definition is 1. Okay. So now what happens if we look at this? Well, what we want to do is we want to write this as a multiple of 4 plus some remainder, because the remainder is going to tell us what this should be. Okay, so can we write this as this power as some multiple of 4 plus some number? And yes, we can. So we can write it as 3 times 4 plus what? Plus 3. And so this is going to be what? Well, it starts with what? It starts with I, -1, negative what? I. So this was going to be -I. So let's see. So since I to the 4th is 1, we write the given power as a product involving I to the 4th, right? That's what I was just saying. So there we go. So we have we want to write 15 as 12 times 4, right? Plus 3, right? But then you can use the property of exponents to split this up into a product, right? And so here, 3 times 4, right there. There you go. So using the power rule, right? Power of a power. And so we know this is equal to 1, and 1 raised to any power is 1. So we know this is going to be 1 times whatever this is. Well, we know that I to the 3rd is what? -I. So this has to be -I. Okay? And that's all you have to do. Okay, -3. Okay, so here we have to treat this a little differently, right? We have a negative exponent. So multiply, we want to multiply this by 1 in the form of I to the 4th to create a least positive exponent for I. We need positive exponents. So how are we going to do this? So we're going to multiply by some power of 4. So we want the smallest power of I that gives us 1, because we're going to multiply by 1, because we don't want to change this. So if we multiply this by 1, we get the same thing. But we can also write 1 as a power of I, right? We know that every 4th power of I is 1. So we want the smallest power of I that will make this into 1, or excuse me, into a positive exponent. So this would be it. So again, property of exponents, if we have the same base and we're multiplying, we add the exponents. So 3 plus a negative, excuse me, -3 plus 4 is 1. So now we know that I to the -3rd power is equal to I. Okay, and that is the end of this video. And again, please make sure you're watching these before class. It's going to help you tremendously. Also, make sure you're practicing these on your own before class. Okay, we're going to do a lot of practice in class, but remember, don't forget, you still have to be practicing these outside of class. And please, 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 make sure you're taking notes. Also, even more important, if you get stuck on something or you don't understand something, and you want me to explain it more, or you have an example, or you're doing some of the other examples in the textbook, which I highly recommend, or you're working on the suggested homework and you get stuck on something, bring that up in class and we'll work through it together. Okay, until then, have a great day.